In 2009, a digital weapon achieved kinetic results, destroying nearly 1,000 uranium enrichment centrifuges in Natanz, Iran. This was not a missile strike, it was code. Stuxnet demonstrated that supervisory control and data acquisition, or SCADA, systems are the critical vulnerability point, where information technology meets operational technology. The attack exploited the fundamental trust inherent in industrial control systems. The goal was simple: manipulate the rotational frequency of high-speed rotors until material failure occurred. This required deep knowledge of both Siemens Step 7 software and the physics of uranium hexafluoride cast centrifuges. The operational disruption was immediate, forcing a significant setback in the target nation's nuclear program, proving cyber warfare can bypass traditional defense budgets and physical barriers. SCADA systems manage geographically dispersed assets, relying on Programmable Logic Controllers, or PLCs, to execute real-time control. The PLC acts as the intermediary between the physical process, like a valve or a motor, and the human-machine interface, or HMI, used by operators. In the Natanz facility, the centrifuges were controlled by Siemens S7300 and S7400 series PLCs. These controllers typically prioritize reliability and deterministic operation over robust security, often lacking modern authentication or encryption protocols. The communication backbone, usually industrial Ethernet or proprietary field bus protocols like Profibus, transmits sensor data and control commands. This architecture creates a single point of failure. If the PLC logic is compromised, the physical process is entirely subverted, regardless of what the HMI displays to the operator. Uranium enrichment relies on cascades of high-speed gas centrifuges, typically operating at 50,000 to 100,000 revolutions per minute. Maintaining precise rotational frequency is paramount, as even minor deviations induce destructive resonance and vibration. The centrifuges are fed uranium hexafluoride gas. The separation factor, which determines enrichment efficiency, is directly proportional to the square of the peripheral speed. Stuxnet targeted the variable frequency drives, or VFDs, which regulate the motor speed. By manipulating the VFDs, the attackers could force the rotors to operate outside their stable design envelope. This manipulation was designed to be subtle initially, causing cumulative damage before escalating to catastrophic failure. Stuxnet was delivered via a highly sophisticated infection chain utilizing 4 separate zero-day vulnerabilities. The initial vector was often a compromised universal serial bus drive, bypassing the facility's air-gapped network perimeter. Once inside the information technology network, the worm used vulnerabilities like the Microsoft Windows Shell LNK parsing flaw and the print spooler service exploit to propagate laterally. Crucially, Stuxnet carried valid stolen digital certificates from reputable hardware manufacturers, Realtek and J-Micron, allowing its malicious drivers to load without triggering standard operating system warnings. This certificate theft was a major legal and technological escalation, blurring the lines between legitimate software and state-sponsored malware.
The core innovation of Stuxnet was its ability to execute a man-in-the-middle attack directly within the operational technology environment. The malware checked for specific hardware identifiers and network configurations unique to the Natanz setup. If the environment matched, Stuxnet injected malicious code into the PLC's memory, specifically targeting the logic blocks responsible for controlling the variable frequency drives. This injected code intercepted the legitimate sensor data, reporting the centrifuge speed back to the human-machine interface. The malware then fed the human-machine interface false, normal readings, ensuring the human operator saw no indication of the physical sabotage occurring in real time. This digital deception maintained operational normalcy, while the physical destruction proceeded undetected. The attack unfolded in 2 distinct phases over several months. Phase 1 involved a subtle, prolonged manipulation. Stuxnet commanded the variable frequency drives to briefly increase the centrifuge speed from the nominal 1064 Hz to 1410 Hz for short bursts. This induced material fatigue and microfractures without immediate failure. Phase 2, initiated after a delay, was catastrophic. The malware dropped the speed dramatically to a destructive 2 Hz, then rapidly cycled it back up to 1064 Hz. This rapid cycling through critical resonance frequencies caused immediate large-scale mechanical failure, shattering the high-tensile aluminum rotors. The staggered approach maximized damage while minimizing the chance of immediate detection by human operators. The Stuxnet incident fundamentally redefined cyber defense requirements for critical infrastructure and the defense industry. The failure of the air-gap security model proved that physical isolation is insufficient against determined state-level actors utilizing supply chain vectors. Consequently, the industry shifted focus to deep packet inspection and unidirectional security gateways, which allowed data flow out of the operational technology network for monitoring but strictly prevent any inbound commands. Compliance with standards like International Electrotechnical Commission 62443, which mandates security throughout the entire industrial automation lifecycle, became a non-negotiable business requirement for vendors supplying control systems to defense and energy sectors globally. From a business perspective, Stuxnet introduced unquantifiable cyber-physical risk into industrial insurance markets. Traditional property damage policies often exclude acts of war or terrorism, leaving critical infrastructure owners exposed to billions in losses from sophisticated malware. Furthermore, the attack raised profound legal questions regarding non-proliferation treaties. If a nation's nuclear capability is degraded by cyber means, does this constitute an act of aggression or a legitimate defensive measure? The ambiguity forces defense contractors to incorporate cyber resilience clauses into all major infrastructure contracts, shifting liability and demanding verifiable security audits before deployment. The market response catalyzed the rapid growth of the operational technology cybersecurity sector. Companies specializing in passive network monitoring using deep learning to establish baseline behaviors of industrial protocols saw massive investment. These systems detect deviations in programmable logic controller communication patterns, identifying malicious code injection or unauthorized command sequences before physical damage occurs. The defense industry now mandates hardware root of trust mechanisms in new programmable logic controller designs, ensuring that only cryptographically signed firmware can execute. This shift represents a multi-billion-dollar annual expenditure dedicated solely to securing the interface between digital control and physical reality.